Okay, thanks everyone for coming. Thanks for everyone on Zoom for virtually coming. And thanks for everyone who's watching this for posterity. I'm very pleased to welcome Sid to the AI Seminar Series. Sid got his PhD from UMass Amherst, where he won the Outstanding Dissertation Award. He then did a postdoc at Berkeley and is now an assistant professor at Arizona State University, where he has received an NSF Career Award and done a lot of great work in the area of reliability of autonomous systems and explainability of autonomous systems. So I'm looking forward to hearing his talk about his most recent work. And with that, I'll turn it over to you, Sid.
Thank you, Reed. Thank you for that kind introduction, and thank you all for coming. It's great to see you all in person as well as on Zoom. So I'm talking about assistive AI. So the first thing that I want to do is ask, what is assistive AI? And we don't have an agreed upon definition of assistive AI, but here's an example. So this is from an NSF project that we did on AI and the future of work. And the idea was to explore ways in which robots could help out humans act as force multipliers in agile manufacturing. Okay, so here the idea is that the user gets a new design and wants these two robots to help him out. And as you can see here, the robots are doing relatively short-term tasks. Right? They're just fetching objects and giving it to the user. But in general, the user can have an arbitrary desired task in mind, and we want the robots or the AI system to help him out. Right? So this is what I mean by the kind of AI I'm looking at. This is taskable AI. There's a task that the user has in mind, and the AI system is supposed to go out and help them. Right? In general, there could be longer tasks. So for instance, the user might actually want the robot to search for a part and bring it, or manufacture a part and bring it. That's all fair game. Right? So intuitively, we can think of an assistive AI system as something that makes it easy for its operators to use it safely. Right? So this is a starting point. It's a principle, not quite a definition, because there are no Booleans here. You could take an input AI system and assess it for different aspects. For instance, how easy is it to use? For whom? Who is the class of operators? And what kind of safety guarantees does it actually provide for this class of operators? And this is a good starting point in the sense it's an aspirational goal for many of today's AI systems. But as we'll see a little later, it's not quite enough. Right? But it's a good starting point. So in this talk, I'm going to focus on how abstractions are surprisingly effective in facilitating different aspects of such AI systems and for going beyond. So abstractions on their own have been discussed a lot in AI, right? And there is no surprise here. There's a lot of work by Reed and Chris. People have been looking at abstractions. Now, one of the major focuses of AI research on abstractions has been on how to use abstractions to make it easier to plan. The intuitive idea being, if I look at a planning problem from a higher level, then I have fewer decision cycles to plan for. So I have a shorter horizon. So if I have to plan for a complex task, I don't have to worry about the robot's joint movements. I can reason at a more strategic level. So that's one of the long-standing purposes for abstraction in AI. Another good reason to use abstraction is that users typically think of goals and preferences at a very abstract level. Right? Unless you're a roboticist, if you have a household robot and you want it to do the laundry, you think, I want my clothes clean. You don't really think about which trajectory the robot's arms should follow. And it turns out from some of our work that abstraction is also surprisingly effective in computing explanations of AI behavior. Okay? So in this talk, what I'm going to do is show you some examples of how we used abstraction and where we found abstractions to be useful for each of these types of uses in AI. So what do I mean by abstraction? So here I have a household robot. Let's say you wanted to do the laundry. So on the left, you see a concrete state description. There's no abstraction here. For every object, I'm giving a specific location. Right? These are the coordinates of that object. You have the robot's joint values. You have the goal specified in a very clear form. So for every object, I'm saying where it should be. And hopefully, these numbers are inside the washer. right? If my objective was to get the clothes in the washer. So this is good. I have enough detail here to figure out robot dynamics accurately. Right? The problem is it does require low-level goal specification. It's hard for a non-expert to get that right. And it's also not very suitable for long horizon tasks. On the other hand, over here, I have a more abstract representation. Right? So here I'm just saying shirt 1, towel 1. These are in some collection of locations, which I'm calling the table. Right? I can specify the goal more abstractly. Everything that's dirty has to be in the washer. Right? Now the problem is here I've lost so much detail, it's not going to be possible for me to figure out what will happen if the robot just extends its arm. So I don't have an accurate model of dynamics anymore, but it's good for long-term reasoning. Right? So this is the overall picture or the type of abstractions I'm going to be looking at. And the problem with abstractions is although we intuitively think of them, they're going to simplify the problem, they do weird things. So here's a simple example. Now, in this case, I have a jigsaw puzzle, and I want that robotic gripper to pick up one of the pieces and attach it to the other, but it has a wall on one side, so I have to be careful. Right? If I pick it up from the right, I have to attach it from the left, and so on. So this sequence of actions works, and let me just use this composition symbol to denote the composition of actions. So it's the same sequence of actions written more compactly. This is a sequence in the concrete state space for this problem. So now let me add some, or consider an abstraction. And this abstraction is going to say, I'm going to ignore the side from where you grasp. All right? And this is where funny stuff starts. So I have the composition of abstraction of actions here. So the same sequence as above, but now I am taking the abstraction of actions. So intuitively, you can think of this as the abstraction of the initial state, right? I don't know which side is the wall in the gripper. I do the pickup, and I get this. Now when I try to attach, I don't know which of these effects is going to occur, right? So because of abstraction, this action attaching has become non-deterministic, even though the concrete domain was deterministic, right? Now I can do this the other way around. That is, I can first perform the composition and then the abstraction, in which case, so alpha is my symbol for representing abstraction. So in this case, I take this sequence, which is the same as this guy, and I abstract the start and the end, and I get this guy, this result at the bottom. Right? So what you can see is abstraction and composition are not commutative here. Right? And this is a very simple case of an abstraction. And the interesting part is that when abstraction and composition commute, you actually get Markovian abstractions. Now, in all of our high-level planning, etc., we assume the domain model is Markovian. Right? It turns out that this condition has to hold for that transition system to be actually Markovian if it was the abstraction of something low level. Right? The sad part is that this condition usually doesn't hold. It takes a lot for this condition to hold, and if you're just designing an abstraction intuitively, chances are it won't hold. So with this background information, let's take a real example. So this is a little more realistic. Here's a task and motion planning problem. It's related to problems like navigation among movable obstacles, etc. You want the robot to pick up the red can. Okay? But you can only grasp things from the side. And again, I'm going to use a very common abstraction. I'm going to forget about the grasp poses. So I'm going to write an abstract model. And this is quite representative of how you might think of abstract models for these kind of problems. It's just saying I have a pick up red can action. But every time it picks up the red can, there are two possibilities. It could either have to stop because there's going to be a collision, or it ends up succeeding. And I've given some probability numbers. The numbers are not too important as long as they're non-zero. Right? These are the two possibilities. Now you can take this and say my goal is to have the red can in my gripper and give it to a planner. Right? Now this is where things get funny. The planner is going to come back with a solution that the proper policy that is guaranteed to reach the goal is to just try repeatedly picking up the red can. That's not going to work here because it's so cluttered, there's no solution path. The robot can't actually execute that. Okay? So in reality, this policy has zero probability of success, but the abstract model that I gave my planner makes it think that it is feasible, that it can just execute this policy and reach the goal. So these kind of observations are responsible for the research field of task and motion planning, right? Where you try to figure out what is the right abstraction and how to do refinement so that you can solve this problem. Now, the interesting thing that's going on here is that this probabilistic effect or non-deterministic effect came because I introduced the abstraction. It was not there in the real domain that I had to start with, right? So it's not a situation where the model is different from the real world. It's more a situation where the abstraction I constructed is imprecise, and the model confuses imprecision with stochasticity, right? So one of the things that we did in looking at this problem is to say that suppose I can keep track of imprecision caused by the abstraction. So I have a known abstraction operation that I'm applying. So I should be able to tell when it's imprecise, right? So I keep track of parts of the model that became imprecise due to abstraction. And then during search, when I'm actually looking for robot behaviors, I will refine it with information from the low level, but only in specific search paths. Okay, and this idea seems to work very well. So we did a bunch of experiments where we tried using different types of planners at the high level, different planners at the low level. And the advantage of this is you can develop the algorithm once and give it different goals, and it finds the complete solutions at the task level and the low level consistently across them, right? So in this problem, for instance, where it's trying to set the dinner table, we didn't tell it to use the tray, right? That's high-level reasoning that the high-level solution presented on its own. So it computed that, and it found out the correct order of stacking of cups and bowls, etc. Okay, so this was good, and we had some formal results that indicate that this is going to be probabilistically complete unless you need high-level plans that don't make sense, right? So it's a pretty reasonable guarantee there, but we are still assuming that everything is deterministic at the low level. So we are starting with a deterministic model and building this. So the thing we wanted to do really was to see if the similar idea of keeping track of imprecision and then refining it incrementally, if it would work for stochastic domains. So now what I want to do is to model my decision-making problem as a stochastic shortest path problem. So this is a variant of Markov decision processes where you have no discounting, you have a cost on actions. So you're primarily looking at finding high probability paths to the goal. Okay? The problem, of course, is if you look at solutions, so this is one solution, one candidate solution to the problem, right? Every time you do an action, you're going to have multiple effects. You might have some probabilities for those. And this is going to be exponential in the horizon of your planning. Right? So quickly, your solutions become very large. And this is just a high-level policy, which means if I have to actually execute pick can 3 here, I need to compute a grasp pose. I need to see if there's a motion plan for it. And then when I'm placing it down, I need to find, again, a put down pose, figure out whether there's a motion plan, and so on. So this becomes very expensive because I have exponentially many nodes here. And it's because of this that most task and motion planning approaches, when they look at stochastic cases, they try to focus on most likely sequences, right? So you produce just one plan, and if it breaks somewhere in the middle, you replan from there, right? So we wanted to see if we can do something in between, right? Not compute just one path, but also not have to compute the entire solution before you can execute. And the hint is in these probabilities. So if you look at some of these action sequences and outcomes, they are very unlikely, right? So what we decided to do was to see if we can balance the likelihood of encountering a sequence of events with the cost of computing plans for those sequences of events. Okay, so that gives us a meta-level knapsack problem, because I have a value associated with every possible sequence of occurrences. The value is the probability, right? How much probability am I covering with that particular trajectory or that particular sequence of outcomes? And the cost is the computational cost, right? So now instead of trying to find a solution policy regardless of how likely events are, what I'm going to do is do a greedy approximation of knapsack, because knapsack is NP hard, and if I try to find exact solutions there, it's not going to help me. So it turns out the greedy solution works quite well, and it gives you a lower bound on the amount of probability mass you're not covering as you go along, as you give it more time. So My student Naman led the charge on this. And here what we're seeing in these results, on the x-axis, we have the time that the planner is given. So this is being run in any time mode. I start the planner and observe how good its policy is over time. The red lines are showing randomized selection of refinement paths or refinement trajectories. Okay? And you can see that in some of these cases, you have to wait for several thousand seconds before it finds the more likely path and jumps up, right? And in most of these cases, it has some sort of an improvement, which you expect, but it's quite slow. In the, yeah?
Can I ask a question?
Yeah, sure.
So in the previous slide, you said, so do you have a heuristic which estimates the computational effort of?
That's a very good question. Yes, we have a heuristic that computes the estimated cost of refining a node. And that heuristic is the amount, the volume of space of the poses that you have to search in.
So just to differentiate, is the heuristic to measure the estimate the computational effort or the cost? Computational cost or the cost?
The computational cost. We are assuming that each action has cost 1.
So is it in general, generally speaking, that extremely hard to estimate for most general domains?
Well, it depends on the kind of domains you have. In these mobile manipulation domains, usually what happens is every time you try to figure out how to pick up an object, you have a volume of space where you're going to sample or search. And that volume is easy to compute. Right? You can also include costs of actions in this and do a utility or expected cost as your value for each path rather than just looking at just the probability. But to illustrate these results, it was enough to look at probabilities. And what you can see here is if you do the meta-level knapsack-based solution, then very quickly you cover the most likely sequences. So what this tells you is if you had an anytime implementation of this like this, then depending on the domain-specific risk assessment, you could start execution before your complete policy is computed. And we did a bunch of other experiments on a range of problems, and the archive version has the full details for that. So now the main question is, well, is it actually useful in practice? So we looked at a class of problems where we are getting the UV robot, we're giving it a target structure of Kiva planks, okay? And it has to build that structure. There's a human who places the next plank, but we don't know where that next plank is going to be placed. So every decision epoch, there is this uncertainty where the next plank is going to be. But as you can see, it computes a policy, and it's quite effective in building these towers. Right? One thing that we found out while doing this is that Kiva planks are not designed for the quasi-static assumption. So we have to get our robot to move really slowly to make sure that these structures are stable. And looking at that is okay, cool. Any questions so far? Cool. Excellent. All right, so everything that I discussed thus far was looking at hand-coded abstractions, right? Somebody wrote the high-level action descriptions for each of these problems. And the next thing we wanted to see is what happens if we don't have this? Because hand-coded abstractions are good, right? If you have a domain expert who knows about the possible tasks for the robot, they can actually quite effectively tell you this is a good high-level action to keep around, and it helps. Of course, a big advantage is if somebody wrote the abstraction for you and your system fails, you can just blame that person, right? So the disadvantage of hand-coded abstractions, of course, is if you don't have a domain expert, or if the domain expert was thinking you're going to use a robot for one class of tasks, but you use it for something else, then the abstraction quite breaks down there. So the question is, can we actually learn these high-level actions, right? And that leads to the question, what do we mean by high-level actions? So looking at some of these problems, we developed this intuition that if you're trying to get from this side to this side, you can think of high-level actions in this domain as entering the corridor, crossing the corridor, and then exiting the corridor and getting to this other goal area, right? And this is an example of a sequence of high-level actions. So in other words, what I'm saying is, in general, you can think of high-level actions as moves between critical regions in an environment. What do I mean by critical regions? Regions that are important or useful in many solutions, but that have a sort of low probability measure if you were to randomly sample configurations from that space. Okay? And if you think of high-level actions, then in general, more generally than just navigation, for instance, picking up this bottle, I just described a high-level action, but the reason we think this is useful is because this state where I have the bottle in my hand is useful for many kinds of tasks. Right? So if I look at a distribution of tasks and try to find out which regions of the state space are salient or important to it, then I can formulate my high-level actions as moves between these critical regions or salient areas of the state space. Right? So the question, however, is can we actually predict what the critical regions in a state space are? So for that, we have to first define it, and we can do that. We can define it very clearly mathematically, but intuitively what you can think about is, suppose you have this kind of an environment, right? You have a rectangular robot, so its orientation is important here, and you generate lots of test problems. Okay? You have the goal on the other side of the wall, and you let a motion planner solve it. And these are relatively small problems, and the motion planners can actually compute solutions to this quite efficiently, so you generate them, and then for every location, you plot the density, that is, how often did the solution use this location. So you get something like a solution density. And what I'm going to say is a critical region, the criticality of a region is a measure of what fraction of solutions pass through it, normalized by the area of that region. Okay? So this area, for instance, over right here in the middle has a very high criticality score, as you would expect, right? It's important for getting by in this environment. Yeah.
It's not clear what you're sampling. You could be using a randomized planner and sampling the same start and end states, or you could be deterministic planner and sampling different start states and end states. I'm not sure what you're sampling.
The sampling over here is, there are two there's the sampling density, which is by default uniform, which is what an RRT would use to sample its intermediate poses. The density I'm constructing here is over the space of solutions that I've computed with arbitrarily selected goals and starts.
That part is not clear. You're sampling you're sampling different starts and goal states, or you're picking an arbitrary start and goal state and sampling solutions over those two states.
At present, I'm not sampling anything. I'm just giving the intuition of what it means for a region to be critical, on how to evaluate it quantitatively. Right, okay. So for that diagram, let me show this. This will make it clear. So here what I'm doing is creating training data for my network to predict critical regions, okay? And how did I generate this? Randomly, I select an initial location somewhere over here, a goal location somewhere over here, well, goal orientation, give that to a motion planner. Ask it to solve it. That gives me one plan. Okay? Then I sample another pair and give it to the motion planner. And I do this repeatedly for my training environments. All right? And now, when I have a sufficiently large population of solutions, what I do is plot what is the density for each of these locations. Right? How likely was a solution to pass through it? Is that clear?
So you're using some form of human intuition to know that the start and the end are on opposite sides of the wall.
That's right. But this is only for training data. In our test set, we throw that away. Right. Now, the interesting thing here is, since we are also, this is a hide-off robot, right, that we wanted to work for eventually. So what we're doing is also plotting the critical regions for different orientations. So here, for instance, you see that this little green patch is indicating the robot should be oriented vertically here. It should be oriented horizontally here. And similarly, for this hinged robot, you can see that the base rotation should be vertical over here and closer to, the angle should be horizontal here and so on. So you get lots of interesting stuff just by looking at training data. There's nothing surprising so far. Right? This is all generated by an existing motion planner, and we're just simply plotting the histograms in some sense. Okay. Now, it turns out we can learn to predict this quite effectively. So these are results from environments that were not in our training set, but we are predicting the critical regions for these different robots, right? So again, you can see it's getting some useful features. Here it's predicting that the robot should be vertical. Here it's predicting that the base rotation for the hinged robot should be horizontal and so on. So it's getting quite useful information. So we were quite excited when we saw these results, and we thought all we need to do now is to seed our sampling-based motion planner with some points from these critical regions. And turns out that doesn't work. The reason it doesn't work is because if I'm over here, and if I plot a point over here for its base location, the robot is just going to try to move this way and hit the wall. So that doesn't quite work. But instead, what does work is if I start simultaneously RRTs or PRMs from each of the sampled critical regions. Okay, and then it builds all these trees concurrently, and that works very well. But remember, so far we are doing just low-level planning. We haven't built any actions. So the thing we really wanted to do is the following. Given a workspace, I predict the critical regions for each joint. I define high-level actions as moves between these critical regions. Now I have a library of high-level actions. Now I just do hierarchical planning. What do I mean by that? Well, I take this set of possible high-level actions, build plans using them, and then try to connect them. The new thing that I'm doing here is even during high-level planning, I'm doing a multi-source search, which means I'm starting searches from multiple points in my state space. In general, this is not a very good idea because it's not easy to find out which states are intermediary, which states are going to be closer to your goal, and which states are going to be further from your goal. This is not possible in general, but here we are predicting that, right? So we can develop this idea, and we took a bunch of testing environments which look quite different from our training set. So we have these smaller rooms which are like 20 square feet or so. And then we had a bunch of larger rooms here, about 3,000 square feet or so. And we also have a bunch of environments where you have a manipulator. It's not a mobile manipulator, we're just using it for the arm in these experiments, right? And run the same basic process, okay? One intuitive thing that is good to keep in mind while looking at these pictures is that every time we generate a critical region, that's a cluster of points, right? It's not an abstract state yet. But what I do to build an abstract state from that critical region is to take that and grow a Voronoi cell around it. Okay? So now my abstract states are going to be Voronoi regions or cells built around these critical regions. My high-level actions are going to be moves between these abstract states. Right? So this is a visualization of that Naman came up with. It's very colorful, so I really like showing it, right? And it's just a visualization, though. The true critical regions are in high-dimensional space. You can't see that easily, right? So these are the abstract states that it predicted or that we generated using the critical region predictions for this environment. And we don't compute these abstract states and regions in a pre-processing step. That would be just too expensive and not quite fair to compare with a planner that doesn't have all this time, right? So we do this on the fly, and we computed a bunch of comparisons. We took lots of planners from the AMPL library. We also took a planner here called Vanilla LLP, which uses critical regions, which we developed in our prior work, right? But doesn't use high-level actions. So it's getting the same learning results, but not high-level actions. And then we have a bunch of different experiments. So R denotes the rectangular robot, H denotes the hinged robot, car R denotes the robot with Dubin's model semantics, the rectangular robot, and then we have the fetch environments. On the x-axis here, we have this time given to the planner, right? So we are just giving one problem after the other, and we're computing how many problems the planner solves in this fixed time limit. Right? So you can see the blue planner, which is the method that I described, is outperforming everything, which is good news. We just kept giving it more and more environments, and it seems to be doing quite well. The interesting thing here, however, is if you look at Vanilla LLP, this is the planner that gets the learning information. So it gets critical regions, it grows simultaneous PRMs. That it doesn't perform as well as this planner that is also getting the high-level actions and performing a high-level search first. Right? So this is quite interesting in terms of results here, that you can learn the abstraction, that's fine. You could do low-level search on these critical regions, but if you learn the abstraction and perform search using high-level actions, you get much better performance. So I saw a couple of hands go up there. That one.
Yeah, sorry if I missed this, but I see how you're generating, basically you have a high-level space graph, right? And I see how you're generating the vertices as these critical regions. How are you getting the transitions?
All possible combinations. So from one abstract state to another, right?
Okay.
Right.
That's not always feasible.
That's not always feasible, that's right. So what we do during the computation here is keep updating a heuristic score for each action, just like you would do in a regular high-level search. Yeah.
I'm a little confused. In the previous slide, the diagram you showed, is that the high-level state space or the low-level state space?
The partitioning there is a projection of the high-level state space. The high-level state space actually cannot be visualized because it's, again, high-dimensional, right? But this is a projection down to this map.
When you're constructing these critical regions, the planner is the high-level planner, or so the states are the high-level states or the low-level concrete states?
The critical regions are low-level concrete states. So we don't start with any abstraction. We given a map, we predict critical regions, we grow Voronoi cells from them, right? And so far everything is in the continuous low-level space. But once I get a cell, for instance, this brown cell over here, I'm going to call it an abstract state.
I see. And in your experiments, what's the degree of freedom for your low-level planning?
So it varies across. So the fetch, I think, has a 7-DOF arm, right? The hinge robot has, base rotation plus the location x, y, so 3 plus the hinge angle 4. So it goes all the way.
The network is making these predictions on these 7 degree of freedom states.
Right.
How much data do you typically need?
About, I'd say about 800 to 8,000 samples, but these are all for the simple environments. We didn't have to generate any training data for these larger environments. We're just reusing, so the environments that I showed earlier, this is pretty much what we had, not this. This kind of environment was what we had for our tests, for our training set. I think we had like 4 versions of something like this, but you can find the details in the paper.
What is the input to that network?
I'm sorry?
What is the input to your network?
The input to the network is an occupancy grid plus the density, the critical region from our training data. That's the labels. All right, cool. So in the interest of time, let's move on from this because I have a couple of other threads to touch upon, and we can come back to this if we have more questions. All right, so the main points that I want to make here are learning these abstract states and learning these high-level actions is not only possible, but it seems to actually do better than just learning at the low level and planning using that, right? And one good thing over here is that we still have probabilistic completeness because we only add a finite number of points to our sampling process. We don't reduce the measure of anything to 0, so in the worst case, you're just going to be doing whatever your previous sampling-based motion planner would do. Okay. Great. So let's see. So remember P1. This was the principle that I mentioned earlier, and I said it's not sufficient. So it's time to go back there, and I want to poke some holes in it, right? So remember P1 was saying that an AI system must make it easy for its operators to use safely. Now this has a major blind spot because of which we run into 2 problems, right? The first is the kind of problems that you see with AI and future work. Right? Because this principle doesn't take the cost of training operators into account, you can easily run into situations where you have an AI system that's perfect with P1, but it is so difficult to operate that most people in the factory are not able to use it. Right? You could also have this extreme version of the problem where nobody on the planet is qualified to use this, and you've got effectively a super intelligent kind of system. Nobody has the knowledge to operate it or to control it or to use it safely, right? So P1, although it's an aspirational goal for many of today's AI systems, it's not enough, right? I think a better way to think about assistive AI is to think of think of it as a system that makes it easy for its operators to learn how to use it safely, right? So the keyword is learn, and we're making it easier for the user to learn about it. And it turns out that abstractions are really good at doing that as well, right? So in the next few slides, I'm going to look at how that is possible. So let's jump to that. Okay, so I showed you this demo earlier where we had the couple of robots helping a human assemble a new design, right? So that was a perfectly harmonious video, right? So clearly the human knew exactly what the robots could do. But let's take a look at, few days before that was made. The user might ask the robot to bring it a certain gear, and the robot might come back with something like, well, first you need to replace everything in its original position, which is naturally going to be perplexing to any person, right? All the more so to someone who doesn't know much about robotics, right? So at this point, the user could provide a counterfactual or a foil that says, wait, why don't you first give me the gear and then do whatever you want? The robot could come back with an explanation that is perfectly correct, but also perfectly meaningless to anybody maybe who's not a roboticist, right? So what this example illustrates is when we have a counterfactual situation or a situation where a user is asking a question about an AI system's behavior, we want an explanation that does two things. First, it should address the user's specific concern. Why can't it do whatever the user asked? And the second is that it should provide an explanation that is easy for the user to understand, right? So in some sense, when I think of easy, the first thing that pops into my mind is, okay, it should be more abstract, all right? But how do we find the right level of abstraction? So now what I'm going to do is generalize our picture of abstractions a little bit so that we can find out a solution for this kind of situation. So now I'm looking at an abstraction lattice. Okay, so what that means is here is a concrete state which has a lot of information for this rover. It has information about where interesting soil samples are, where rock samples are, and so on. Now you can consider different types of abstractions that ignore different types of detail. So here you lost information about rocks, there you lost information about soil, and so on. And you can build a full lattice. On the top you have the most abstract model. Okay? Now the hypothesis is when you have a user who's not quite sure how the robot operates or how the robot operates in a particular environment, their understanding is one of these abstract models. We don't know which one, right? So there are two things we need to do here to find an explanation. One, find out, okay, which of these models is closer to the human's model? And two, what information do I need to provide to help the user to understand why their solution is not valid? So here's what we can do. Initially, we have that abstraction lattice, right? And the green zone is the area where we think the human's model is. And this can be arbitrarily large to start with. Now, the user asks a question, right? And every question you ask tells me what you are thinking about, right? So it gives me some idea of your mental model. In this particular case, when the user says, why can't you do a certain sequence of actions? It tells me that the user thinks that that sequence of actions is possible and useful, right? So what I do is use that information to reduce the space of possible human models because I am looking for models where pi is consistent. Now that gives me a smaller area of the lattice. And by lattice properties, what I can prove is if you take a supremum of all of these models here and compute information required to go out of that green zone for that guy, then it'll actually work for all. So I don't need to find explanations for every possible model. I can find an explanation for the supremum model, and that's going to work. So what I do is find out what is the minimum detail I need to add to one of those models, the supremum model, to reach a model where pi is inconsistent. Okay, because that is going to be new information, and that helps us compute an explanation that is user-specific and also refutes the specific foil that we had. So this approach works quite well, and we did a bunch of studies, and it turns out that you can also use this to explain why solutions can't be found or to summarize policies. And we just had a journal paper come out of this. Sharath has been doing the heavy lifting in all of this work, and I highly encourage you to take a look at this. What I'm going to do now is switch gears once more for the last time in this talk and look at a more general case of this problem. So far, I've been assuming that I know the model of the robot, right, at the lowest level, even if I don't know the abstraction. I know the model of the robot, and I've been assuming that the user has a specific question. But if you think about how household robots might be deployed, most users, 95% of the people out there, might not know about AI. So they might not even know which questions to ask, right? Because they're faced with this new technology. And furthermore, most of these deployments will be black boxes, right? There could be a number of reasons for that. You have proprietary software. The company is not just going to tell you what's the internal of it. It might not even be clear what it is. And either way, what we want to do is figure out whether it is safe for a user to use this household robot that we say is taskable for a certain task, right? So there are two challenges in doing this. One is things change, right? You might have an autonomous car, it gets an update, and now it no longer behaves the way it used to. So is it still okay to do parallel parking using this car? It was working yesterday, you got a new update, right? Is it okay for you to go off-road with it now? How do you tell? That's one problem. And in these situations, what we'd like to do is, if I had a good assessment of this vehicle, if I understood what its capabilities were before, now something changed, can I do a differential assessment so that I don't have to figure out all the capabilities again from scratch, which can be very time consuming. So this is one aspect of the problem. The second is that an AI system goes far beyond its primitive actions, right? So let's take a very specific case here. Let's say you have a game playing AI system. It controls this hero character here, that's Link, right? It has to slay the monster, get the key, get out of the door, right? So what are its primitive actions? Just the keystrokes, right? Move up, down, left, right, interact. Those are its primitive actions. Now, regardless of how good your game playing agent is, those remain the primitive actions. However, what a user might be more interested in, what are its capabilities in a broader sense, right? So this is just the functionality. The capabilities take into account the planning and learning algorithms that this guy might be using, right? You might train it on a very good data set, you might improve its performance. Primitive actions remain the same, but capability changes. So the question that comes up here is, how can we discover high-level capabilities of an agent in ways that a user can understand it, right? Now, we can fall back for intuition on the quintessential black box scenario where you have two humans trying to figure out what their capabilities are. And in this case, you'd run an interview, right? You'd ask questions, you would understand what their capabilities are. But the thing changes quite a lot when you have an AI system as one of them. It's no longer going to be clear which questions to ask. And AI systems have different generalization modes, different failure modes. So it's not even clear how to extrapolate from their answers. So what we really need is a well-designed AI that conducts this interview process for us, for the user, specific to the user, right? And works with the black box system and tells the user what its capabilities are. So this is very much like the OBD tool. So if you've ever seen what your car goes through in the garage, first thing they do is plug in a device. And regardless of the manufacturer, this device gives you a bunch of status reports, what's going on with the car. So we need something like that for our AI systems, right? Because it's not making assumptions about internals of a car. But the problem is taskable AI is much more general in its functionality than a car is, right? And it's going to change more frequently. So what kind of requirements do we need to place in our design of black box AI systems so that, first of all, the requirements don't make specific requirements on the internals. So we want to not throttle innovation. What kind of requirements can we make that are non-intrusive but still help us assess AI systems? So here's an example of a requirement. What I'm going to assume is an AI system can be hooked up with a simulator. This is usually possible. That's how we test them, right? And it can take a query and give me a response. A specific form of query is a sequence of instructions. Again, AI systems satisfy this. They have to tell me what instructions they can take, otherwise I can't use them. And the response is going to be, well, I can execute case steps of your instruction, and at the end, the simulator says I'll be in this state. Right? So very simple interface, not requiring anything from the internals. Now, my overall picture is I have this AI system which could have arbitrary internals. It doesn't know about the user's vocabulary, doesn't reveal its internal implementation. And I want to build this intermediary assessment module. This thing should interact with the agent and figure out what the limits and capabilities of the system are. Okay, so let's see how we're going to do that. Firstly, we're going to use this particular formal language to come up with interpretable models. And this might be familiar to many of you. It's just saying a precondition and effect kind of description for capabilities. And it's very easy to convert these kind of models into things that look like natural language. Here, for instance, it's just saying if the gripper is empty and object is on table, then executing the pickup action will have the object in the gripper and so on. So these are interpretable models, right? The disadvantage is there are too many of them. So we have to do effective search. And this is where an interesting trick comes in. So again, I'm going to look at the abstraction. At the top, I have the most abstract possible space, but now the space of what I have here is the set of all possible models that could hold for this agent, right? And I'm going to look at functionalities to start with, so just primitive actions. Every time, what I try to do is figure out how a particular term appears in the precondition or effect of an action. So for instance, hand empty can appear as negative, positive, or absent in a precondition of a certain action. Each of these denotes a huge class of possible models. Okay? Now the clever thing here is we take pairs of these models and tell a planner to generate a sequence of instructions so that these two models disagree. Okay, so I get a sequence of instructions, I give that to the agent, and I look at the agent's response. The agent's response can only be consistent with one of these models. That's how I generated the query. I use that to prune away a huge class of possible models, and I keep repeating this. And Pulkit led the charge on this, and it turns out this method works very well. Right? So on the x-axis here, I have the number of queries. On the y-axis, I have the accuracy of the learned model. Right? And I'm comparing with a baseline that is observational learner. That is, it looks at observations of agent behavior and tries to infer what its functionality was. And as you can see, it doesn't always converge. It's not a system that can perform causal inference because it's not doing any interventions. Right? On the other hand, our system converges and it's often faster. Right? So this is how we can learn functionalities without any knowledge about the internals of the system. And it works very well when your system is deterministic. Right? So now let me address the other thing I talked about, differential assessment. So you have an initial agent, and you have a drifted version of that agent. It went through some updates or whatever. Something caused it to change. This is your initial model of the agent. Right? Now, after the change, you get a very small number of observations. And the question is, can you query this guy, the drifted agent? Can you re-infer its model with a fewer number of queries? And it turns out that this method can be used because once you get a small number of abstraction observations from this drifted agent, you can get a hint as to what might have changed. And then you start the query process focusing on those changes. And these purple regions here show the amount of accuracy that you can recover with a very small number of queries. That's the blue line over here. Okay. All right, so the interest of time, I'm going to skip a bit and go back to the problem of discovering agent capabilities, because that's what we started with originally. So let's say that's my scenario. I have, again, a pixel-based state. I have an AI agent, so it has primitive actions, plus it has some learning module, whatever. It follows its own policies. I don't know which policies it follows. So what I'm going to do is let the agent run for some time, okay? And that's going to generate a sequence of low-level states. Every time it gives me a low-level state or a pixel image like this, I'm going to use the user's vocabulary to express that as a bunch of features. And I'm going to treat that as my abstract state. So this state, for instance, has P0 at a certain cell, and it's next to the monster, right? Now, again, I'm going to use the user vocabulary, let the agent run. It executed this particular action using its internal policy, which maps to the same abstract state. So nothing happens here. So I keep doing this. This one is also in the same abstract state. At some point, the agent executes an action that gets it in this state, where if you'll notice, the monster disappeared, right? So this is a change that is expressible in the high-level vocabulary of the user. So I treat this as a high-level capability, that the agent can go from a state that looks like that in the user's vocabulary to a state that looks like that. So that's a high-level capability. I'm going to record that, okay? And every time this transition occurs at the abstract state space, I record that as a high-level capability and then query the agent about these capabilities rather than the primitive actions. So using this method, what we can do is effectively discover capabilities. So here's an example. We started with something like this, we end with something like this, and in the middle, the agent could have been doing any of these. So this multiple actions, primitive actions can lead to these transitions. So we saw some of that data. And from that, our system discovers this capability along with when you can apply it and what the results are. And if you spend a few seconds looking at it, it's not that hard to follow. You can transcribe it automatically into something like this. This is basically the kill monster capability that it discovered on its own. The system discovered on its own. We are not calling it the kill monster thing because it didn't come up with those words, right? But you can read this, and it makes a lot of sense. And the method is quite scalable. We tried it on a huge, on 4 different domains from the GVG AI repository. It works with different types of agents. We looked at the discoveries. They made sense to us, which is not very surprising maybe. So what we wanted to do was to see if it makes sense to real people who don't already know about the system, right? So we ran a couple of studies. The first study was assessing interpretability. So in this study, we asked the user to look at the generated description and try to match it with one of the summaries. And there were 2 summaries that didn't correspond to anything, right? And we found that surprisingly high fraction of matches were accurate, right? So capability CI is actually summarized by summary SI, so they all got it right. There was some confusion here, but it's very minimal, right? So this tells us that it is actually interpretable. People can understand what it does, but it doesn't really tell us whether they're useful. So the second study, we gave the users, the study participants, a sequence of high-level capabilities and asked them, well, do you think the agent can use this sequence to go from one state to another? So they have to do analysis with the capabilities. And we found that if you compare analysis using primitive actions versus analysis using the discovered capabilities, the blue bars here express the time taken to answer the question. And the orange bars here represent the time taken to answer the question using capabilities rather than primitive actions. So you can see it's always the users answer questions faster, and these plots here, the boxes indicate the accuracy of the answer with capabilities. And you can see that also doesn't drop. It's usually higher than the accuracy using functional description. So it indicates that people understand this and they're able to answer questions about agent behavior more effectively. Okay, so I'd like to stop here. The main takeaways that I want you to get from this is abstraction seems to be really useful in computing policies, explaining policies for assistive AI systems. There's a lot of work still to be done. We are still scratching the surface here in learning actions. The stuff that I showed you later on with discovering capabilities was for deterministic agents. So we have to see how to get beyond that to stochastic environments, and we're working on that. So hopefully I'll have more updates on that soon. With that, I'll stop. This was joint work with fabulous collaborators. Thank you.
We have time for questions, including those on Zoom. How does that work? They can speak with one of the app. But how do they take their turn? We just try to stop them. Okay. So there's one in the room.
Yeah.
Yes. Could you help me see the kill monster capability again? Because it didn't really look to me like that capability, because there seemed to be some absolute positions involved. Usually
Yes.
kill monster, I would expect it to be like, if the monster is next to me, then I can stab it.
That's a good point. Yeah. So this is the kill monster capability, but it is grounded.
But is the monster always at that cell?
No, it's saying if the monster is at that cell, then you will be able to kill it. So there's a precondition that says at M153.
But I think what he's saying is it's not abstract, because if you found the monster at a different cell, this wouldn't hold, and you'd have to learn that capability. So I guess I don't see that it's an abstraction.
So it is an abstraction compared to the pixel-based domain that we start with. That is the only information we are getting here from the agent's simulation, right? It is a capability in the sense you can still have this agent perform that sequence of actions to go from this state to that state. You can do it. Now, there are two problems if you want to generalize this to the relational setting. The first is I could take all of these symbols and lift it, but I'm not guaranteed that the agent will actually be able to do that in the more general setting. So I don't want to make that generalization because it might be false. The second is I have to collect all of these kinds of capabilities, and my purpose is to see if you can actually execute it, right? If the agent can actually execute it. So you have to sort of collect all of these capabilities and then generalize them and sort of merge some of them together if you can. Currently, we provide very strong guarantees with the discovered capabilities. They are maximally consistent with the causal accuracy of even future observations that you might get, because we are in a deterministic setting. So we are never going to show you a capability that could be made inconsistent by future observations. So for those strong guarantees, I can't generalize beyond this right now. I could generalize it and then say, okay, there's a chance it might be incorrect. Yeah.
What if the domain was that there was a pit to the left of the monster moved to the left and was dead, so now it's not alive and you're not next to the monster, but there's no actually causal connection between the actions of the agent.
Right.
So you were describing this as a causal inference, and I'm not sure that you can
but
get
your
causality from...
Right, so your example is not deterministic. Because for different moves of the agent, the monster moves on its own, right? So this is, at present, only for deterministic settings, right? But at present, we are looking at the non-deterministic, the stochastic case, and then our guarantees are going to suffer in that case. We are going to have to say that, okay, sometimes this is going to happen, sometimes, as you'd expect in a stochastic domain. But I think we can still ensure causal accuracy in the sense that when I do this, here's the set of possibilities that's going to occur. And, the system that we're using for this is Halpern's actual causality rules. They are, they are covering a pretty general setting, so I'm hoping that we'll be able to extend it there. Good, thanks. Thanks for the questions. Another? Yeah.
I'm curious about, so it's really interesting that you can synthesize this type of abstraction. I'm wondering how, to what degree it will align with people's previously existing abstractions, and sort of how you're thinking about maybe an alignment problem between what the robot considers abstractions that are actually have the symmetries that you would expect in the real space versus what people would actually expect.
Right, and this is something that bothered us initially, so which is why we formulated in this way. The that intermediate level is getting the user's preferences. So these are the terms that the user understands, and in some form we are expecting their definitions. So for instance, in that case, holding X gripper, I want a functional definition of that term that I can test in a simulator state. This is where holding X gripper holds, this is where it doesn't hold. Maybe it's a classifier, but I need some of that information. So the alignment with the user is coming from that side of the input.
What do you do then if the user's abstractions don't transfer well?
Yes, that's a good question. So in this case, what's going to happen is the model that you learn is not going to be perfect, right? So you can have situations where the vocabulary is not sufficient to cover the actual thing, and then you have to express imprecision again. So we're back at that level where you need to say that there is something more precise here. I could either explain it to you what this concept is and then give you the correct model, or in your vocabulary, this is the most accurate you can be.
So if, sort of in general, you can sort of, what I'm taking from your work is you can have, the first part of the work is the robot system generates its own set of abstractions from the space. And then this is sort of, the humans have their own set of abstractions.
Exactly.
And this is a way to map the state into the human's abstractions.
That's a very good way.
Either correct or sort of, it doesn't, is there anything you could say about how well they overlap? And it sounds like if they don't overlap at all, this transfer doesn't actually help you.
Yeah, in general, I would assume they won't have a perfect overlap, right? Like you saw in that colorful picture, they weren't all rooms. So I'd be hard pressed to logically describe to you what a particular abstract state means. But you can have a translation going back and forth. You could train classifiers, for instance, that say, okay, this thing that you think of, this quadrant of the area maps to roughly these states. And I'd have to go from there, right? So that is a part of the problem that we haven't addressed yet. Good, thank you. Any other questions? Yep.
You're not fully understanding this part. So you give an example here about holding with a gripper. So can you talk a bit more about the different level of abstraction there? Like you could have an example where holding with a gripper versus grabbing a water bottle. Yeah. So can you talk a bit like how you do with that, and then what does it mean to like understand?
So think of these terms as classifiers over the real state. Okay, and all I need is a way of telling whether in a particular concrete state that property, that feature holds or not. As long as you can tell me that, I can explain the model in your vocabulary. Right? So I need a one-way dictionary in some sense. Any other questions? Yeah.
So my question is unintended side effects. So your earlier example that the robot said that it couldn't pick up the gear because it would, but it can, and it can tell the person that I'm able to accomplish this. But doing so, and it would fail to mention these side effects, and I don't see how you can know that those side effects are not intended and therefore are okay.
That's right. So we're assuming in that part of the work that the utility function is clear. Which parts are okay to go to, which parts are not okay to go to. And if you have that, then side effects are just actions that have some of these unwanted effects. But the broader, I think the semantic question that you're getting to is sometimes users might give the system a goal and not expect that the robot would follow a certain policy. And we haven't quite looked at that aspect of the problem here, because it involves figuring out what is the human's projection or expectation about possible effects, which effects are different that will actually occur, and which of them are significant to the user. Because there are going to be lots of side effects, not all of them are even...
I would imagine that in real world situations, that dominates your translation from what the human is, the vocabulary of the human, to what the AI thinks those terms mean.
Right, and so in ongoing work, we've been thinking about how to detect relevance of features, which is related to this. In some cases, I care about how close the robot is getting to a certain gear, and I might not want it. But while I'm doing some other tasks, like if it has to pick up that gear, I expect it to go there, right? So it's very context and task dependent, and I should be able to predict that somehow. We don't have very good answers for you at the moment on that, but it's ongoing work. Yeah.
So kind of follow up on what you just said. So there is no way of knowing how the system did it, right? So an example someone gave me I really like is like you're cleaning a room. So instead of you ask whether the room is clean at the end, and then the state won't be able to distinguish I just push everything under a table versus I actually clean the room. Is that accurate here in this example? If I say clean room, the room is clean, is the query that I ask.
Oh, in this case?
Yeah,
Well, in this case, I want the state with respect to all the features. So if there was a feature that said things are under the table, then I would expect you to tell me that. In fact, I'm not trusting the agent to do, the black box agent to do that translation into user terms. My system is doing that. So the agent just gives me the simulated result, the simulator state, which could be in any old format. I have a way of recognizing which features hold there. So if the user tells me things being in these locations is important, then I will know that from the state.
So we got the edge cases, right? Like, so the cleaning example, if I just say the room is clean, those two are both acceptable. Is that accurate?
Not if the agent already knows the locations are significant to the user, right? In that case, I will get that information in my final state.
It seems to beg the question. So you're saying that the user doesn't really understand the capabilities of the AI agent, and so their vocabulary is unlikely to include those nuances that it's unlikely to include those nuances. So user says clean the room. The robot has certain ways of cleaning the room, one of which is to actually put stuff away, and the other is to push it under a table, as he mentioned.
Well,
and the person doesn't know what the robot it doesn't even. I don't understand how you can get from the user vocabulary to the AI assessment module vocabulary.
So that part is well defined, right? I have a user vocabulary. When I say I have the vocabulary, I mean that given a concrete simulator state, I'm able to test which of the predicates hold in that state, right? Now, there are two separate things: understanding the capabilities versus understanding what's important to you, right? So I'm assuming the user knows what is important to them. So in this particular example, if it is important to the user that certain things be in certain locations or not be in certain locations, I'm assuming they know that, right? How exactly you access the full set of vocabulary, the full user vocabulary, there are multiple ways of doing that. One is to have an extended dialogue with the user and give them plans and say, is this good, bad, why not, and, that sort of acquisition. The other is you could say that with this kind of vocabulary, I'm going to find you good plans, but maybe you don't understand these concepts, and I'm going to give you some training for that. So you can have wrappers that are outside of this particular piece that explain to the user the concepts that they need to understand capabilities precisely. But both of these are different questions, right? On the one hand, we are thinking about, does the user know what is important to it? And on the other hand, we are thinking, can we discover the agent's capability in those terms? So this is looking at the latter question, right? Suppose the user knows, can I figure out how to describe the capabilities in terms that the user tells me? Any questions over Zoom?
They usually speak up if they do, but there's about 10 people on Zoom.
Okay.
I can ask a quick question.
Mm-hmm.
Can you hear me?
Yes.
Yep.
Okay. Questions about the learn critical regions part here, Doug. I'm assuming that you didn't use the 2D match to learn critical regions for the fetch arm.
No.
Any details on what training process for that was?
Right. So we got an occupancy grid in whatever the high dimensional workspace was, and our training labels were telling us which bin of each DOF has a high enough frequency. Right. So the training process is to generate lots of plans using some sort of a curriculum of training data, and to do that only in a small workspace so that the motion planner can do it realistically.
critical regions are, I guess, joint angles for each of the joints of the arm.
The dimensions
they
are the
different
joint
wavelengths
angles.
in-
Yeah, the dimensions are the joint angles. Imagine a huge high-dimensional representation where each dimension represents a different joint angle. You create some sort of bins for them and then mark them up. First build a histogram for how many solutions pass through them, and then do a cutoff, a threshold, and keep the ones with the highest. Roughly with that. But all of the source code for all of the work that I discussed, except some of the last 2 threads, is publicly available. And do send me an email if you have any questions about how specifics of any of that was done.
Okay, thanks.
Sure.
All right, well, let's thank Sid again for